Hi everyone! In this video we're going to talk about exponential functions. So exponential functions are very specific types of functions that the base is the number and the exponent is a variable. So normally in the past you've seen functions where the base is maybe x and the exponent is some number. This is not that case. This is the opposite. So exponential functions are any function where your base is a number, specifically other than 1 though. We tend to not use that number 1. So some base raised to a variable exponent. Alright, so let's take a look at this one where we have f of x equals 3 to the x power. We're going to graph this exponential function by finding a handful of points. Now I'm just going to pick a few different numbers for x to plug in, and it's good to pick negative and positive numbers. Let's go ahead and put, let's say, 0 right here in the table, kind of in the middle. And then let's pick 1, 2, and 3. And then -1, -2, and -3. Now I'm plugging in each of these numbers into the exponent position, because that's where the variable is at. And so let's start in the middle. This is 3 to the 0 power, and any number to 0 is 1. Other than 0 to the 0. Every other number to the 0 power is always 1. So then if I plot that point, I plugged in 0 and I got out 1, which is right there. Let's plug in 1. 3 to the first power is just 3. So I plugged in 1 and I got out 3. Plot that point. Plug in 2. 3 squared is 9. So if I plug in it's 2, I plugged in 2, I got out 9. That's actually way up here, not even quite on our grid anymore. And I can't draw this one, but I'll write it. 3 to the third power is 27. So that would be way up off the graph. And now, or off the grid. Let's go with some negative numbers. -1, 3 to the -1. You do have to remember some stuff about exponents, and if you've never seen this, I'll just tell you really quick. A negative exponent is just telling you to move the base. And in this case, it's technically in a numerator because there's no denominator visible. So this is 3 on bottom, and then that -1, you take off the minus sign. So it becomes 3 to the first power on bottom, and then 1 over that, because there's nothing. It's not that there's like nothing left on top when you move the 3 down, it's that there's a invisible 1 left on top. Let me show you real quick with the next one. So we have 3 to the -2 power, and so that negative exponent is just saying that you should move your base 3 down to the denominator, or wherever it's at. If it was already in the denominator, we would move it up. So we move it, and then the minus sign comes off. And then there's nothing left on top other than an invisible 1. So this becomes 1/9. And so what's going to happen on this next one, we have 3 to the -3rd power. And so using this same idea, 3 to the -3rd power is 1 over 3 to the +3 power, which is 1 over 27. Now let's plot those last few points. We had -1 that we plugged in, and we got out a third. 1/3, if you need to use a calculator, you'll see that this is about 0.3. So it's not very high up on our graph. It's maybe like right there. 1/9 is even smaller. That's like 0.1. So when I plug in -2, I'm even closer to my x-axis. 1/27 is even smaller. So when I plugged in -3, that's like way down here. Now here's our graph. If I draw to connect these points, I want to be careful because it looks like this graph is like coming down to the left. However, it will never go lower than the x-axis. So when I draw my graph, I kind of have to make sure I don't draw it any lower than the x-axis. And I'll explain in just a moment why. And now this is the graph of our function 3 to the x. Now, here's why we don't go any lower than the x-axis. Think about any number you can possibly plug in here. If I pick a huge negative number, like negative 1,000 or something, it's just going to be 1 over 3 to the positive 1,000. And so it's just a really tiny number, like 0.0000 something, but it's never negative. So we actually stay up here. And so what we call this idea where we get super close but don't ever touch this axis is that there's an asymptote. So there's an asymptote here on the x-axis that we're getting super close to, but we never really touched this. So this function has an asymptote. So let me write that for you. It has a horizontal asymptote at the x-axis, which is the line y equals 0. All right, that is our first exponential function. Now, exponential functions, they have very interesting behavior. They actually model real life situations fairly often. One example is population. Population grows exponentially because it starts off really, really slow with just a few people, and then more people are born and so on, and then it just shoots up. So populations follow exponential growth. Another thing that follows exponential growth is viruses. Viruses follow exponential growth. Bacteria, they start slow and then they just spread. Now, on another example, the next one, I'll show you kind of the opposite of what this graph looks like. So let's answer some questions. What is the domain of this function? And so the domain is the inputs. You can plug in anything. You will always get a real number out if you plug in any real number. So you can plug in anything from negative infinity to positive infinity. All real numbers. Will the y values ever be negative? What is the range of this function? We already talked about that. No, you're never going to get a negative number out of this function, because even if you pick a really huge x number, or really huge in the negative numbers for an x number, you're going to get like 0.00 something. It's never going to turn negative magically. It's always just like 1 over 3 to a power. So with that being said, your graph, the lowest it ever goes is 0, but it never touches 0. And then it starts at 0 and goes up to infinity. So the interval notation goes from 0 to infinity for the range. And then because you never actually equal 0, you put a parenthesis. If we equaled 0, we would put a bracket. Okay, let's see. As x approaches negative infinity, what y value does the graph approach? Okay, so just think about this for a second. X is going to the negative infinity numbers. So x is getting smaller, but in the negatives. So it's going this way. So as your graph goes left, what's happening is what the question is. As our graph moves left, x goes to negative infinity over here. What's happening to the function values? Well, they're getting super small. They're getting really close to 0. The y values approach 0. As x approaches positive infinity, what do the y values approach? So positive infinity is this way. X gets bigger and bigger and bigger. Well, look what's happening to your graph. As you plug in bigger x numbers, your graph, your function values are like shooting up. So they are going up to infinity. Okay. And then is this function increasing or decreasing? Well, definitely increasing, because it's growing. It's going up to the right. It's going up as x gets bigger. Is it 1-to-1? So 1-to-1 functions, you plug in one x and you get out one y, and then that's the only time you'll ever see that y value. One x gives you a different y. Another x gives you a different y. And so you can tell by starting to draw horizontal lines. Let me see with just a ruler really quick. If I start with horizontal lines, it's only going to touch my graph once, every horizontal line I draw. Even right here when it looks like this might be a horizontal line, if you could zoom in on this, like if you use maybe a graphing utility, it's just getting super close to 0, but it's actually different numbers every time. It's like never really touching the x-axis. And I'll show you an image on the computer in just a moment so you can verify that this is not really horizontal right here. So the function is 1-to-1. So here's the graph I was just talking about. This is the graph of 3 to the x. And if you zoom in, it's not actually ever touching the x axis here when y is 0. So even right now it looks like it is, but watch. If I start to zoom in, the closer I get, it's really not ever going to touch it. It just gets way closer, closer and closer. So if I move over, even though it still looks like it's touching, zoom in more, and we see it's not touching. Okay, so it's a really small y value, like 0.000 something, and you can go all the way forever and you'll never actually equal 0. Let's try this next function, g of x equals 1/2 to the x power. So this is a different exponential function because the base is different, but it's still an exponential function because the base is a number and the exponent is a variable. So let's go ahead and pick the same x values. You can pick any x values you want, but for graphing purposes, these are going to be good ones for us to draw. So now, let's start in the middle. We're going to plug in 0 for our exponent. So 1/2 to the 0 is just 1. So we plugged in 0, we got out 1. Right there. 1/2 to the first power is just 1/2. So plugged in 1, got out a 1/2. Plugged in 2, 1/2 squared is 1/4. So 1/4 is a little smaller down here, half the size. And then let's do one more for positive x. 1/2 cubed is 1/2 times 1/2 times 1/2, which is 1/8, which is even smaller right there. Okay, let's work on the negative ones. So if I plug in -1 for my exponent, well, let's kind of explore that really quick. We have a negative exponent, but this time our base is a fraction. So remember what I said a minute ago on the last example, the negative exponent is telling you to move your base. So in this case, the 1 is in a numerator, so the 1 is going to have to go to the denominator, and the 2 is in a denominator, so it's going to have to move to the numerator. And once you move the base, the minus sign comes off. And so this just becomes 2/1, which is just 2. So that whole thing was just 2. Let's do the next one. 1/2 to the -2 power. Well, the 2 moves up, the 1 moves down, and then the minus sign comes off. So this just becomes 2 squared over 1 squared, which is just 4. And then one more. We have 1/2 to the -3 power, which is 2/1 to the +3 power, which is 8/1, which is just 8. Okay, let's plot those points. So we have -1, and our output was 2. -2, our output was up here at 4. -3, our output was way up here at 8. And this time, if we draw this, our exponential function looks a little different because it's actually going down to the right. But it's actually never going to touch the x-axis again. There is an asymptote there. So this function, what's the domain? So the domain, it's actually all real numbers again. You can plug in any real number and you will always get a real number out. Will the y values ever be negative? No. There is this asymptote once again that you can pick any x number you want and it will never turn your outputs negative because it's just basically moving around the 1/2. It's either 1/2 to a power or you flip over 1/2 and then raise that to a power. So there is an asymptote there. So will it ever be negative? No. And so the range, this graph, the lowest y value is really close to 0, never touches 0, and then goes all the way up to infinity. As x approaches negative infinity, what do the y values approach? So as we're going this way, left, as we're plugging in negative x numbers, what's happening to the graph? Well, negative x numbers getting plugged in makes the graph go up to infinity. Well, what happens if you plug in positive x numbers as x goes to infinity? So as x goes to infinity, look what's happening to the graph. It's moving really close to 0. So y is 0, is what it's approaching. Is the function increasing or decreasing? So this time it's actually decreasing because it's going down to the right. And this one, very similarly to the last one, it will only hit every horizontal line at one point. This is 1 to 1. Now, let me explain really quick. This is still an exponential function, but this is considered decreasing. So this still represents real life situations, like if bacteria was a cure for disease or something, or bacteria was under some kind of control, it would be out of control, but then it would have this effect. It would just all the way decay toward 0. Okay, so exponential functions reflect a lot of real life situations. So now, recall from our first page that we graphed the function 3 to the x. Let's graph its inverse. So, we don't even know what the inverse is, first of all, but we're asked to graph it. Now, in order to do that, we have to remember what we learned about inverse functions. In the next video, we're going to learn how to find this inverse, but for now, we're just going to graph it. So let me remind you, let me show you what our graph looked like, okay, and the points that we found on it. Okay, so here was 3 to the x and our points. So for the inverse of a function, remember what we talked about, the values, the input and the output switch. So what was x becomes y, what was y becomes x. So I'm going to take our same numbers from 3 to the x and just swap x and y. So we had plugged in the following x values, so these are now the y values. Okay, so these 7 numbers are our outputs. And what came out of our function is now what we're going to call the inputs. So when we plugged in 0, we had got out 1. So for the inverse, we plug in 1 and get out 0. When we plugged in 1, we got out 3. So now for the inverse, we plug in 3 and get out 1. And that happens for all of these. 9 gives us 2, 27 gives us 3, and then 1/3 gives us -1, 1/9 gives us -2, and 1/27 gives us -3. So let's see what this graph looks like. I'm going to start in the middle here. 1, 0. So 1, 0 is right there. 3, 1 is here. 9, 2, it's kind of off of my grid here, but I'll still plot it. 9, 2 is here. Now, I can't plot 27, it's just too far off, but that's okay. -1 comes from 1/3. So 1/3, we got to fit a lot of points right in here, because this is 1. 1/3 is in between 0 and 1, so 1/3 is like right there, and then we go down to -1. Okay. 1/9 is even closer to 0, and we go down to -2 as our output. And then 1/27, even closer to 0, we go down to -3. And so this graph looks like this. And this is the inverse. Oops, it should have been a little closer here. This is the inverse of our exponential function. And what we're going to learn in the next video is that this is actually what's called a logarithmic function. So let me show you, because we've learned this previously, this graph and its inverse, the original, reflect across a certain line. So look at this graph, and then let me move this out of the way. So this is our graph, and if I were to reflect across the line y equals x, if I can kind of do it with my paper, I'll fold it. If I were to fold my paper right there, I would get out this graph. So the mirror is the line y equals x, which is this line where you have 1, 1, 2, 2, and so on. So our original graph was here, and then it reflected to make this inverse graph, this inverse function. Now let's answer some questions about it. What is the range of this function? Well, the range, it's a little different this time. the range, look at your graph. If I go back up, if you look at the graph, the y values are the range. The y values go all the way down to negative infinity, and over here they're eventually going to go up, gradually up toward infinity. So the range is all real numbers this time. The graph goes all the way to negative infinity, all the way to positive infinity if it keeps going up. And then you can tell from our table here, you can plug, you'll end up getting any y value out, any real number. Will the x values ever be negative? So looking at the graph, just looking at it, what do you think? The graph, here's my y-axis, x is negative over here on the left. Well, no, we're never actually going to pass this y-axis. So no, the x values will never be negative. And it's because of where they came from. We plugged in negative numbers in the original function and we got out only positive numbers. So when we swapped our values, none of our original outputs were ever negative. So now the inputs for the inverse, what we're calling the inputs, it's never going to be negative. And so there's also an asymptote on this graph, and it happens to be the y-axis this time. So this one has an asymptote on the y-axis, which is the line x equals 0. What is the domain of this function? So what kind of numbers get plugged into this function? Well, if you look back at your table, it was actually only positive numbers because of where they came from the original function. But you can also tell from the graph. This graph, the x values that this graph covers, they're never on the left of 0. So they're actually only 0 and bigger, not even including 0, because we never actually get to plug in the number 0. So what will the domain be? 0 to infinity. And then, how do the domain and range of this inverse relate to the domain and range of the original? So they're exactly swapped. Okay, so let me make that a little bit more mathematical. The domain of this inverse, so the one we just graphed, the domain of the inverse, which was 0 to infinity, that was the range of the original graph. And then the range of this inverse that we just graphed, the range, the outputs of what we just drew, negative infinity to infinity, that was the domain of the original function. Okay, and that should make sense hopefully because it is inverse functions. A function and its inverse, everything switches. So domain becomes range, range becomes domain when you're dealing with a function and its inverse. And so this is the new part, and we'll end here with this one, and then we'll cover this in another video. This inverse function, f inverse of x, is called a logarithmic function. We shorten it usually with the word log. You could say logarithmic every time, it's just a lot of people say log. So if you hear log function, it's the same thing. And then the equation of this inverse function, and we'll get into this in the future, is y equals, but you can use your f inverse notation. So f inverse of x, I just want you to see that it's y, but it's more specifically f inverse of x, log base 3 of x. Okay, so you don't have to know how to find this just yet. I just want to show you that what you just ended up graphing a moment ago, this graph is the graph y equals log base 3 of x. That's the function. Okay, so that's it for this one.